So last time we already talked about this. Okay. And we talked about, rearranging this. Maybe R equals V over I equals V over R. And so essentially you're just using algebra to rearrange the terms. But, however you want to learn it, this is the basis for everything that we do. Okay. So we talked about this a lot. We talked about these two things in the first couple of lectures, right? Voltage and current. And so we spent, almost 4 hours on just this alone, right? How to identify resistors, what is a resistor and what's its purpose, and what are the different types. We talked about fixed resistors where you buy, you can look on the color code and tell what it is and what the tolerance is. We looked at rheostats, which is essentially just something like a slider where you have one resistance output. We also looked at the 3-terminal, right? Where you could have a resistance here, and those both add up to the total that's on the outside. Okay? And then we started to do some schematics like this. Okay? And we just had some resistor value, we have some source value, and then there's some current that's generated. Okay? That's if you just have one sort of load hooked up to a battery or something like that. Okay, most circuits are never this simple. Okay, but that's the basis of what we're doing. And then if you just wanted to put off to the side here, the total current times the total resistance. Okay, and you could alternately write this as V total. Okay, so Ohm's law is true not only for the entire circuit, so we use this for the entire total analysis, and we use it on a component basis. Okay? So I can talk about the total voltage in the system, or I could very specifically be talking about this one right here. So, R1 equals the current through R1 over the voltage drop across R1. Okay, now in this case there's only one resistor, so it's connected directly to the source. So whatever this is going to be the voltage of R1. And since there's only one current, the total current is also the current through R1. Okay? Now, once we start adding other resistors, we're going to have to make the distinction between the two. Okay, and the subscripts here, I know this is kind of a R1, R1. Okay, so the subscripts are going to be very important about how I say, talk about the total voltage versus an individual voltage drop, okay, or an individual current through a branch. Okay, that'll become important with parallel. Okay, I'm going to go ahead and erase this. And I'm going to put a circuit back up here. Okay. So the other concept that we're going to talk about is as the current makes its way around this circuit, and here's my source, here's some resistor value. As my current makes its way around the circuit, okay, it's going to encounter this resistance, and it is going to, because it's holding the current back, right, it's going to resist against it. And so to slow the current down, this thing gives off energy in the form of heat. Okay? And so we say how much power is consumed. Okay? How much power is consumed? Okay? When you think of power, you probably think of, probably one of two things. You probably think of horsepower, or you think about power in terms of like how you are charged for your home, right? You're charged by the kilowatt hour. You're not charged by how much voltage you use. You're not charged by your current that you use. You're charged by a combination of the two, okay? And so to find this energy, power is equal to volts times current. So the power dissipation of any one component or the whole circuit is a combination of the voltage across it and the current through it. Okay? So, we don't do anything in horsepower in this class. That's more of a mechanical engineering term they used, when they're talking about motors. So typically we are talking about watts. Okay? So watts equals volts times current, or watts equals volts, I should say, not like that. Watts equals volts times amps, if you just wanted to look at the units. Okay? So if you know how much voltage there is, if you know how many amps there are, then you can figure out how much power consumption there is in a given component or a given circuit. All right? Now, I'm going to go ahead and erase this, so if you need to, pause it right now in the on-demand. Okay? And then go ahead and look at how we can exploit. I'm going to put this up in the corner here. Okay. How do we bring resistors into the calculation? Okay. Do they have an effect? And to that end, can we size them a certain way so that we don't burn them up? Right. That's probably important, that we don't want our resistors catching on fire if we design a circuit. So, what size to keep it within a certain current range. But then we also want to know, how big should the resistor be? Should it be a quarter watt? Should it be an eighth of a watt? Can we get away with that? Or do we need a whole watt? How much current and how much voltage are being dropped across that resistor? Okay. So if I use my algebra skills, I see that voltage is equal to current times resistance. Okay. To this, I get P equals this. I can also rewrite that to say I squared times R. So we can also find the power consumed without even knowing what the voltage is. I mean, technically we do, because we know the current and the resistance. But if you wanted to just talk about the calculation, these are both valid ways to get there. Okay? So let's rearrange this and try again. How about I equals V over R? Now what if I take this and plug it in in this original equation here? I get P equals V over R times V. I end up with V squared over R. Okay? So by using Ohm's law and what I know about it, because these are the same voltages, right? I could be talking about the source voltage, or I could be talking about an individual component voltage. And so, obviously that's going to affect what this is. Is this the power, the total power, or is this an individual component power? Okay. But now I have 1, 2, 3 ways to solve that. Okay. So I'm going to write all this up in the left-hand corner here to reference. So we have Ohm's law. We have, I believe that's called Watt's law, but I just say the energy equation. But we can also say P equals I squared times R. We can also say P equals V squared over R. Okay, so those are our 4 equations. All right, any questions? Let me come over here to the chat. So, any questions? Okay, so basically all I've done here is just set up the equations that we're going to use. Okay, let's keep on trucking. So if you have more than one resistor in a series circuit, let's go ahead and just look at a 2 resistor series circuit. Okay. A series circuit. Okay. So So how would you know the difference between a series circuit and something else? Well, a series circuit has only one circuit path. Okay? It's a loop. Just one loop, no branches. Okay? So you can see here, if we follow the current out of the positive terminal of the battery, remember, the long is the positive and the short side is the negative. So our current is going to go this way, okay? And it only goes in one direction. There's only one loop. It does not branch off. When it comes here, it doesn't split, okay? It only has one circuit path, okay? Because there's only one path, that means that there's only one current, okay? If I generically say R1, R2, and source voltage, okay, I can say that the source current, the current that comes out of the source, is the same as the current that goes through R1, which is the same as the current that goes through R2. There's only one. And so if I ask what's the current of this, and this, well, if you found one, you found them all, okay? And so you can we'll verify this when we actually put numbers on this to see if that's true or not, okay? So hopefully it's true. So only one current, different individual voltage drops. Okay? So we're going to find that in a purely parallel circuit, it's just the opposite. All of them have the same voltage drop, but they have different currents. In a series circuit, there is only one current. They all share the same, but you're going to have this equal the voltage of R1 plus the voltage of R2. Okay? You can't create or destroy matter or energy, right? It only transforms into something else. Okay? And so as we're dissipating the power, it gets dissipated as heat in this case, all right? But if we have a total voltage, and let's go ahead and put a number on here and say 15 volts, okay? I cannot have 7 volts across here and 9 volts here because somehow I created an extra volt, okay? Extra volt, okay? And so you can't do that, all right? You can't create matter and you can't destroy matter. You can't create energy and you can't destroy energy, right? You can only make it something. So all of the individual voltages have to add up to the total voltage, okay? And so we have, I'm going to go ahead and erase this, so if you need to, go ahead and pause it if this is on demand, okay? And erase that. And that principle is known as Kirchhoff's voltage law, okay, or KVL for short, okay? And so more generically, if we write it mathematically, it's the summation of all of the voltage rises minus all the summation, whoa, I just invented a new Greek letter. The summation of the voltage falls has to equal 0. You can't create or destroy matter. Okay, so basically it's restating Newton's, third thermodynamic principle, I think it is. So all the voltage rises, in other words, the batteries or the power sources in the circuit, whatever total voltage they produce, has to be equally divided, not equally divided, I shouldn't say equally divided, has to be distributed such that all of the individual voltages add up to the total, okay? So that means if I have a circuit, and this is 9-volt source, and it doesn't really matter what these values are, I have a drop here, and I have a drop here, and this is where my 0 is down here if you wanted to put a ground in, okay? So this is 0 volts. So we have 9 volts to 0 volts. So I have a voltage drop here, so this potential voltage is higher than this one. This node voltage is 9 volts because it's directly connected to this 9 volt terminal here. That's positive 9 volts on that terminal. That means this node voltage, if you were to put your black probe on this node and you were to put this probe on ground, you would measure 9 volts, okay? So that's what it means to have a node voltage. You're always referenced to ground. So what is the number at that point? Not what's the voltage drop across, that's a voltage drop. I'm talking about the node voltage, which this one is here. This one down here, this entire node, all of that up to here, this is all one node, okay? And so all of that down there is 0 volts. So whatever my voltage drop is across here, I subtract that from what I started with, and now I'm at a lower potential, okay? But now that becomes the high potential of this resistor, and so I have another voltage drop. And those two together had better add up to 9 volts. So if I measure that this is a 5 volt drop here, okay, well, I know that 9 volts minus 5 volts equals 4 volts. So this has to be 4 volts, okay? This is the node voltage over here, 9 volts. I don't want to be confusing. 9 volts, okay? I have a 4 volt drop, which means that 9 minus 4, this node voltage is 5 volts, okay? Now, obviously, 5 volts to ground, I'm going to have a 5 volt drop across this resistor, okay? So I'm satisfied without even knowing what these resistor values are. If I measure this one, I know that this one has to be 4 volts, okay? Any questions on that? John says, I always remember them by ear pie. What the heck is ear pie? Wait a minute, let me try to figure this out. Ear pie. Nope, you're going to have to explain it to me. I see an R, a P, and an I. The E's must be for, okay, I see it. No, I don't, because the P is for power, the R is for resistance, the E are for voltage. What is the A? So what is ear pie? Let me see if it's up here. Ear pie. Like this? No, that can't be it. Oh, I got it. That's Ohm's law. And that's power. Did I get it? I think I got it. So EAR is voltage equals current times resistance, and power equals current times voltage. I got it. Ear pie. I love it. I'm writing that down because I am a sucker for pneumatic devices of all kinds, as you'll see throughout this course. Ear pie, Ohm's law, and power. See, there you go. I learned something. Okay, ear pie. Any other questions? It's pretty good. I don't usually get stuff like that. I usually hear about all this stuff. This must be new age. Okay, so let's keep going here. So let's now go ahead and one of the examples that's in the PowerPoint that I want to illustrate here is thinking about this in terms of a staircase, okay? So, like as you're going 1, 2, 3, 4, 5, 6. So there's 6 resistors here, okay? I have a total source voltage. So initially, as I'm going around my circuit, I rise, and let's call this 20 volts, okay? So now I'm at 20 volts, and so now I go through that first resistor and call this voltage R1. So I go up this direction, now I come down VR1, and now I'm here, okay? I go through the next one, this much down, VR2, and then here's VR3, And maybe this one's a really short one. Okay, so somebody might trip on this staircase since they're not all the same height. But I'm just trying to illustrate this here. So VR4, VR5, and VR6. And so there's 3, 4, 5, 6. And then you come back to here. So this is VR4, VR5, VR6. Okay? So essentially that's what's happening throughout the circuit, and how big this is determined by the resistor size. Okay, but I like this illustration because this is, I'm going this many, I have this many volts available. The voltage of R1 takes this much, so I have now this much available. R2 takes that much, and so now I have this much available. And then R3 leaves me with this much, and then so on until you're down to 0. Okay? Let's go ahead and do a full example here. And I think what I'm going to do, okay, I'm going to write the circuit up here and then do my work underneath. So here we go. Okay, I got 3 resistor series circuit. And I'm going to do this one with nice values. I'm going to do 200 ohm. I'm going to do 400 ohm and 800 ohm. Okay. And let's make this a nice round number like 10 volts. Okay. So go ahead and write that down. So a 10-volt source, 200 ohm resistor, 400 ohm resistor, 800 ohm resistor in series. Okay. So in our Ohm's law up here, I said that you can look at either the whole circuit to find the total circuit current, or you could find an individual circuit current. Okay. So there's like 3 methods of attack you could go here. You could find the total resistance first, then find the total current, and then find each individual voltage drop. Okay? Another way, I'm going to show you here shortly, is with voltage division, where you would find, based on the ratio of each individual to the total resistance, you can find all the voltages first and then find the current. Okay? So there's multiple ways that you can attack this. All right? I think the easiest way to do the series circuit is the following. First, find the total resistance. Okay? In a series circuit, so this is series, total resistance. The total resistance is always R1 plus R2 dot, dot, dot. So R sub n. However many you have in series, you just add them all together. Okay? So if that's the case, 200 plus 400 plus 800. Okay, so there's 600. So I have 1.40 kilo ohms. Okay, because I want to report that in engineering notation, right? We talked about that. So 600 ohms plus 800 ohms is 1400 ohms. So if I were to type in 1,400 equals on my calculator, which is already set in engineering mode, then it's going to go ahead and spit out 1.4 times 10 to the third. Okay. And so if that's confusing, go back and look at our lecture where we talked about engineering notation. Okay? So I have a total resistance of 1.4K. Now I can find the total current, or the current, because there's only one. So the total current is 10 volts divided by the total resistance, 1.4K. And I should have had my calculator out here. Let me get into my calculator app. 10 divided by 1.4K gives me 7.14 milliamps. Okay? So I've just found the total circuit current, but I've also found the current through the 200 ohm, and I've also found the current through the 400 ohm, and I've also found the current through the 800 ohm. Okay? All of them are the same because there's only one. Okay? Now, for the individual voltages, Okay, I know the current through each one, and so I just take the current times 200, the current times 400, current times 800. Okay, so the voltage on the 200, if I separate myself here, voltage on the 200 equals 7.14 milliamps times 200 ohms. Switch back over here and make sure there's no questions as I go. Okay. So 7.14 milli times 200 ohms. And I get 1.43 volts. Okay, so there's where part of it goes. Now I'm going to look at the voltage of the 400. Okay, now, because I know algebra so well, and so do you, you may notice that we're getting ready to double the resistance. So, if there's only one current, right, and now we're looking at a different resistance value, and it's double what my previous one was, this voltage had better double as well. Voltage and resistance, if you look at the equation, voltage and resistance are on opposite sides of the equation. That means that they are directly proportional. If I double the resistance, I double the voltage. That has to happen. Okay? Voltage and current, same thing. If I have a fixed resistor and I put 20 volts as opposed to 10 volts across it, I should get a double amount of current. Okay? It's a directly proportional relationship. If my voltage is static, let's say I'm using a 1.5, or if I put two AA's together and get 3 volts, that's a static 3 volts. Okay, that doesn't change. If I change my resistor value and I make the resistor value go higher, because they're on the same side of the equation, the current has to go down. Okay, those are called inversely proportional. So if they're on the same side of the equation, inversely proportional. If they're on opposite sides, then they are directly proportional. So think about that as you make these calculations, okay? If you don't see that this one is roughly double, or it should be exactly double, then you may have made a calculation in one of the two places, okay? So 7.14 milliamps times 400 ohms. And yes, I'm going to punch this in on my calculator while we're doing this, even though I know what the answer is. Oh, 2.86, which is what I expected, right? Because it's just twice that. Now, the next one, I specifically chose these as in doubles, right? So 200, twice 200 is 400, twice 400 is 800. So now I should be able to see, what is that, 5.6-ish should be my next voltage. So let's try that. Voltage 800 equals 7.14 milliamps times 800 ohms equals, and yes, I'm going to type this out, 5.71 volts. Okay. All right. Well, now the first thing you should check is, now that I have my total current, I have each individual voltage, do my answers make sense? Okay. So here's the first thing I look at. You can see as I increase the resistance, right, because we've already figured out what the current is, so with each new equation I'm increasing the resistance. So the highest value resistor in a series circuit should always drop the most voltage. The least, the smallest resistor should drop the least amount of voltage because they're directly proportional, okay? So, it looks like that's satisfied. That's my first check. My second check is, if I add this, plus this, do I get the total source voltage? So I'm going to do that now. So 1.43 volts plus 2.86 plus 5.71. And my calculator, okay, it tells me exactly 10.0 volts. Okay? Now sometimes you'll have like 9.9, or you might have 10.1 or something, and that's all due in how you round this. Okay? So there's times when everything gets rounded down and it's short, or everything gets rounded up and it's just a little bit above. Okay? But if you get like 10.9 or 10.5, you did something wrong. So go back and check your work. Okay, so those are my 2 checks that I do. Now I still could have set this up wrong. What if I wrote 04 over here instead? These all would still add up to 10, but I had all 3 wrong numbers. Okay, so I still have to set this up properly. It's not foolproof. Okay. All right, now I'm going to go ahead and erase. So what I'm going to do is up here in the corner, because I don't want to erase everything yet, I've got 7.14. I'm writing down what we know. The 200 was 1.43 volts. The 400 was 2.86 volts. And the 800 was 5.71 volts. Okay, now I'm going to erase the rest of this because I want to keep those values handy. All right, I'm going to do 2 things. I'm going to calculate the total power, and then I'm going to calculate each individual power. Power of the 400. Power of the 800 ohm. Okay. So for the power total, it's always the voltage total times the current total. And so I've got 10 volts times 7.14 milliamps. Okay, so figure out what that is. 10 times 7.14 e negative 3, and I get 71.4 milliwatts, because remember, power is in watts. Okay, so if you have 71.4 times 10 to the negative 3, you still use the same prefix. That doesn't change, okay? You just have to make sure you get the right unit because this is supposed to be in watts, okay? Now, at the individual level, this still applies, okay? So the power the power dissipated by the 200 is the voltage across the 200 times the current through the 200, okay? Which is just, the voltage is 1.43 volts times 7.14 milliamps. And so that's going to give me 10.2. All right, that could be right. Let me think here first. Oh yeah, that's total. That's right. 10.2 milliwatts. I was wondering why it was so much different, but that's the total. These are the individual. Separate them out there. Okay, the next one. The voltage across the 400 times the current through the 400, which is, the voltage was 2.86 volts times 7.14 milliamps. And that gives me 20.4 milliwatts. And then finally, the voltage across the 800 times the current through the 800, which is 5.71 volts times 7.14 milliamps. And that gives me, holy smokes, that's not right. Okay, here we go. So this is 40.8 milliwatts. Okay. All right. So, again, if it has a higher value resistor, it has more resistance and is going to dissipate more power. So the highest value resistor should have the highest power dissipation, and it does. Okay. The other check for series circuits, the total power consumed in the circuit is equal to the individual power consumptions. ... P sub n, if you want to go generic. However many of them you have. Okay? So I'm going to take 10.2, whoops, clear this out, clear. 10.2 plus 20.4 plus 40.8. 71.4, which is good because that's what we found up here. Okay? So it's always going to be the individual powers add up to the total power. Okay? Any questions? So Steve asks, will we always round to the hundredths place? Not necessarily, because if we were working with bigger numbers, let's say that this was 100 volts, okay? Or let's say it was 500 volts. I could have a voltage drop of 468. The thing is we always just want to go to three significant figures, okay? So that could be 468, that could be 46.8, that could be 40 or 4.68, okay? So it's always just a matter of three significant digits, not always hundredths, okay? And then John asks, could we not have solved for the last one and just found it by subtracting the total volts, or is it best to solve for all and the double check? So I think what you're saying is you found 200, you found 400, and you're confident in both of those, and so you just add them together and subtract them from our original 10 volts, okay? Okay, you could do that, but I like to do them all just to be sure, okay? Because like I said, especially in a situation where you're taking an exam or something, or you're in a timed quiz, if you're confident, go right ahead, but I will always do these as, unless I can't, I will always try to do them all worked out, okay? So I would say that it's better to do them all and double check, but like I said, if you're confident, then absolutely you could have just added those together and then subtracted that from 10, okay? But I don't suggest that. But I'm not going to tell you not to do it. I'm just going to say you shouldn't, probably, okay? Any other questions here? So Steve says, when I type in the calculation 10 divided by 7.14 kilo-ohm, that's because you should be, this is 71.4 or 7.14 milliamps. So you're taking, so to find the current, you take 10 volts divided by 7.14 milliamps. Okay, so that's going to give you kilo on the top side. So this is something else I like to point out that can make some of the calculations make more sense. Okay, if in this case here, okay, if I have volts and I have milliamps, okay, there's a 90% chance that this is going to have to be kilo-ohms, because this is -3, and this is +3, right? 10 to the -3, 10 to the +3. They cancel out to give you no prefix here. Same thing if I say volts equals microamps, 90% of the time you're going to have mega ohms, because this is 10 to the -6th, 1 millionth, versus 10 to the 6th, which is millions, okay? And so the 10 to the -6 and 10 to the 6, because you're multiplying them, will cancel and leave you with regular volts. And you could take it a step farther, even though we don't really go this far. You could say nanoamps times giga-ohms. Okay? So same thing. 10 to the 9th, 10 to the -9th, they cancel to give you regular volts. Okay? Here's something else to keep in mind. If you have millivolts, and you have a current times ohms, more than likely you're going to have milliamps here, right? Because the milliamps times the amps times the ohms gives you the volts. But 10 to the 0 times 10 to the -3 gives you the 10 to the -3. Okay? So just some little things to keep in mind when you do this. All right? Okay, so hopefully that helps. If not, let me know if you have any other questions. Okay? Whew. All right. Now, I'm still going to leave this up here No, I'm not. I'm going to do a different one. Let's go ahead and move on to a different, and I'll show you the method for voltage division. Okay. So with voltage division, we can find individual component voltages without first calculating the circuit current. Okay? So again, if I want to separate the definition from the title up here. So voltage division, you can find individual component voltages without first calculating the circuit current. Okay? It's based on a ratio of the individual resistance to the total resistance. Okay? And the generic formula we use looks like this. The voltage of the individual component, whichever one it is that you're talking about, that's why there's an X, equals the total source voltage. So you could write VS or VT here, depending on the semester. Sometimes I use those interchangeably, but I'm always talking about the total source voltage here. Okay. And so that's going to be times the individual resistor that we're talking about. Right. This is the same thing. The voltage across resistor A. So this would be VS times resistor A over the total resistance in the circuit. Okay? All we're saying is if we have VS, we have some percentage of it that goes to any one resistor, right? 16%, 23%, because this is always going to give you a decimal, right? It's always going to be, a ratio is always going to be less than 1. So, whatever the, if we had, we had 200, 400, and 800, okay? So in the last one. And so the total is 1.4K, but this ratio is going to be 200 over 1.4K, 400 over 1.4K, and 800 over 1.4K. And I think that better illustrates why the bigger resistance gets more of the voltage. So let's go ahead and do this. Okay. So that's the generic formula, and we're going to use this multiple times. Okay, so if you have to, go ahead and pause if you're on demand, and I'm going to go ahead and erase this. So this is a method you will have to learn because we will use it extensively in the second half of the class, or the second third of the class. So let's do another. This time we'll go with a 4 resistor series circuit. Why not? And this time we're not going to use nice values either. We're going to use real component values. So let's do a 14 volt source, and this is a 2.2 k ohm resistor. This one is a 330 ohm. So this is k ohms. This is a 4.7 kilo ohm resistor, and then this one is a 3.3 k ohm resistor. So go ahead and write that down. And again, I don't write it up here, but it's always implied in my circuits that the ground is here on the negative terminal. Okay, if it was somewhere else, I would let you know. The default for all of my circuits is that we're putting a ground here. Okay, and so essentially this is the circuit. We're taking the 14 volts from there, and then we're going to ground. Okay, I write this up here because it makes it easier, but essentially we're also pulling this negative terminal down to ground on the supply. Okay, so just like this. All right. So go ahead and get that written down. Oh, and Steve says, I didn't use my parentheses correctly. Got it now. Very good. I'm going to jump inside and refill this, or maybe just grab a ginger ale. Hang on 1 second. My refrigerator's right here. Okay. Man. right, so let's do this. Now, regardless if you use voltage division or not, first move is always to find the total resistance, because if you're going to use voltage division, you have to know it anyway, right? So we've got 2.2K plus 330 plus 4.7K plus 3.3K. Right, so 2.2 kilo ohms plus 330 ohms plus 4.7 kilo ohms plus 3.3 kilo ohms. I'm going to go ahead and do that now. And give me three significant figures. And I get a total of 10.53, and so I'm going to round that to 10.5 kilo ohms. Okay. So 2.2, 0.33, 4.7, 3.3 gives me 10.53K. Okay. So now I'm not going to find the total current, even though I could. I'm going to go ahead and find the voltage of the 2.2K ohm resistor. All right. So remember, the individual voltage equals the source voltage times the ratio of the individual resistor to the total resistance. We're taking a percentage of this total source voltage. Okay? So 14 volts times, here is 2.2K ohms over 10.5K ohms. And you might notice that these are both in kilo ohms, and so you shouldn't have to worry about the exponent when you type it in. You should just be able to do 2.2 over 10.5. But if that's confusing, just do it with the kilo ohms. So I get 2.93 repeating volts. Okay. So let me go to the 330 ohm. Now this is 330 ohms. This is going to be the smallest one, over 10.5K. You can see that percentage right there. 330 over 10,500. It's a very, very small percentage. Okay. So this one I punch in as 0.33 divided by 10.5. And there I get 440 millivolts. Ooh, nothing across that one. All right, now I'm going to keep moving around here. I'm going to go to the 4.7 kilo ohm. So 14 volts times. Now I've got 4.7 kilo ohms over 10.5 kilo ohms. This is getting a little close together here. Separate them out. I'm not working with as much space as I'm used to. Okay, so 14 volts times 4.7 divided by 10.5, 6.27 volts. So I think I'm probably on the right track, because this is roughly 10 volts, and so I've got 4 volts roughly to go. So now the voltage on the 3.3K, 14 volts times this is now 3.3K over 10.5K. So 14 times 3.3 divided by 10.5, and I get 4.4 volts. Now my check, 2.93 plus 0.44 plus 6.27 plus 4.4. And that gives me 14.04 volts. If I round that down to the three significant figures, it gives me 14.0. Okay? Any questions on this? Let me type it in here. Okay, so that's, series circuits. It doesn't matter if we have 50 resistors in series or if we have 2. The approach is exactly the same. You find the total resistance, and then you can use voltage division to find all the voltages. So John Perkins says, so you always said 3 significant figures. Yes, for everything you deliver to me, that is the default, 3 significant figures. The only reason I would say differently is that, he said, how are you typing that inf so fast? I've been doing it for 20 years now, so that probably has a little something to do with it. If you teach this class, geez, I've taught it now probably 25 total times. You can wake me up at 3:30 in the morning out of a dead sleep and say, give me 20 minutes on voltage division, and I'll come up with answers, because it's just, you do this stuff so much. So maybe I should slow down my calculations, because I realize I'm probably just floating through this because I'm so used to doing it. So maybe I'll slow down my approach. If you want to test yourself as I'm doing this and see if you can achieve the same answers, okay? And John says, just for the final answer, yes, I keep, whatever my calculator spits out, I just keep using all of that until the final answer that I get, and then that's what I don't round as I go, okay? Now, when you enter for the quizzes, sometimes you have a numerical entry to make, and so let's say that this was a quiz, and I told you to give me the voltage of this in volts. And so you just give me the answer. I would expect you to type 2.93 because that's what answer you got, right? If you used a little bit different rounding, you could have gotten 2.95 or you could have gotten 2.92. So when I put this stuff into Canvas to auto grade, I have to put in a tolerance. And so I would say probably from 2.9 to 3.0. Anything in between there would be good, okay? And I also do 2.90 and 3.00, okay? So even when you report, now in Canvas, if you were to put in 2.9 versus 2.90, then it's going to look at that as the same thing. So if there's a 0 there, it's going to count it right if that's the actual answer, okay? But I would hope that you would just get in the habit of always doing 3 significant figures. And the reason why we do that is if you start looking at the statistical analysis of numbers themselves, okay? And I realize that some of your calculators, including mine, I have, 6 digits? And so I could have a number like this. 321.6521734. Okay, actually I have 6 available. Okay, so my calculator could spit this out. All right. Who cares what's going on down here, right? Because what matters is if we're talking about something at this magnitude, then none of that stuff has any influence whatsoever. It's always the first 3 that the most significant digits always affect the total number, the answer, okay? And so these 3 digits right here influence the answer, and this stuff down here, if we're talking about a purely theoretical calculation, okay, your calculator spit that out, go ahead and write all the numbers, okay? But it's meaningless because when you go to actually build that circuit, it's going to be these 3, the top 3 digits that are influencing how this affects the circuit, okay? All of this stuff, you could put in one 1K resistor, put in another 1K resistor, and again, you're probably going to get even a little deviation right here. Maybe one is 10.4 and one's 10.5, okay? But this stuff down here doesn't matter at all. So that's why we always stick with these 3 significant digits, okay? Even when I was in calibration and metrology, it always killed me when a device had an accuracy of, let's say, in one range it had plus or minus 0.01, let's say. So that's the accuracy of the device. And the display only does 1 digit. How can you give me that accuracy if you're only going to display one of the digits? It's against the rules. You have to, whatever the resolution is, it's going to dominate whether what your accuracy is or not. And so, the best that you could do with a resolution like that is 0.1. Okay. So anyway, any other questions? This is the kind of stuff that I loved to do in my old job, was to get down into the nitty gritty of, the science of numbers and why you would use 9 digits as opposed to, we had an 8.5 digit multimeter. It was a $25,000 multimeter. We could see 1.325613, and ours was good to plus or minus in the millionths. And so in our measurements in our lab, these were important because the accuracy the tolerance is down here. That's how accurate the machine was. That is unbelievable to have that kind of accuracy, okay? So anyway, okay, I don't have any other questions. I'm going to go ahead and I'm going to off to the side here, put these values. So the 2.93 volts, 440 millivolts, 6.27 volts, 4.4 volts. Okay. And now what I'm going to do is I'm going to go back to that original circuit there, and we had 10 volts, 1, 2, 3, 4. And this was, that was 2.2, 330, 4.7, 3.3. Okay. All right, so that was our original circuit. So what I'm going to do now is I'm going to go ahead and find the total circuit current and then see if our voltage division matches. Hopefully it does. Okay, well, again, the total is going to be 10.5 kilo ohms. That didn't change from what we did before. The other way we did it was to say, okay, now I'm going to find the total circuit current, which is 10 volts, divided by 10.5 kilo ohms. So more than likely, I'm going to get something in milliamps here. Let's see. No, I get something in micro because the ratio of 10 over 10.5 is less than 1. So yes, this is in micro. Okay, so 952 microamps. Okay. All right, well, the voltage on the 2.2K, we had 2.2 k ohm resistance and 952 microamps. Let's see here, so 2.2 times 0.952. And we get 2.0, let's see, 2.09, is that right? Do I have these numbers right here? Did we use 10 volts here? No, we used 14 volts, that's why this isn't correct. 14 volts, I apologize. 14 volts, that means this is going to be different. Whoop, 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 whoop. 14 divided by 10.5. That's what I get for not keeping it up there. 1.33, how about that? That sounds a little bit better. Now I'm in the milliamps. Okay? So now, 2.2K times 1.33 milliamps. 2.2 times 1.33, I get 2.93. And the voltage of the 330, so 330 ohms times 1.33 milliamps. I don't think we're going to get to, yeah, we should have the millivolts here. So that's 330 times 1.33 negative 3, and I get 439 millivolts, which is awfully close to 440, right? And then the voltage of the 4.7K, so 4.7K times 1.33 milliamps, 6.25 volts, and the 3.3. Oops, I just did it again. I just blew through all those. I'm sorry. Well, there's only one left. I'll let you do this one. How about that? Sorry about that. I get so excited. I want to find the answer. I like solving these puzzles. 1.33 milliamps. Okay. What do you think that one is? All right. Now, part of the reason why I'm able to punch that in so quickly is I am not using the K or the M, because I know that those are going to cancel. That just like that shortcut I showed you earlier, if I have any kiloohm times milliamps, I just take the first two numbers times each other. So all I'm punching in here you can see this. So this is one of those things, again, if you're doing good the way that you've got it, then don't change it. Okay? You can see there I'm not using any powers on any of this stuff. Okay? Now, sometimes I have to, like the 330 times 1.33. That's not kiloohms times milli. So you can see the second one up there in my history. Yes, I did use a power. But all the rest of them, I'm just taking the coefficients out in front because, 2.2 K times 1.33 milli, the K and the milli are gonna cancel. So all I need is the digits, the value, 2.2 times 1.33. So I just want to point that out. That's part of the reason why I'm doing this so quickly, is because I'm noticing that I have, milliamps times kiloohms. Well, I know that's going to cancel, and so I sort of take a shortcut when I punch it in. Okay. So 3.3K times 1.33 milli, and Steve gets 4.3, and hopefully that's what I get, because we got 4.4 last time. So 3.3 times 1.33, because kilo times milli equals 10 to the 0. So the other way to type this in would be 3.3 times 10 to the third times 1.33 times 10 to the negative 3. And I come up with 4.39. So yes, 4.4 works. 4.39 volts. And this marker is already starting to go on me. I can't believe it. It's only been a week. But I guess these are 4-hour sessions too. Any questions on that? Okay. All right, well, let's have some audience participation on this one. So I'm going to create a circuit, and I'm going to tell you what I want you to find, and I'm going to give you a little bit of time to do it on your own. Okay? And if I'm pretty confident that you all are giving me good answers, then we may go ahead and call it a day. And I will get started on the other work for the labs and finish those up. All right, let's work with some big numbers here. Why not? Just for fun. I don't know what kind of system this is, but that's what's nice about theoretical calculations. It doesn't really matter. 500 volt source. 500 volts. And I have oh geez. What should we do? Big voltages will have some big resistances as well. How about 9.7 mega ohm, 4.3 mega ohm, and 2 mega ohm. So there's a lot of resistance there, but there's also a whole lot of voltage. 500 volts. Okay? So I want to know the following. I want to know what is the total current. I want to know what the voltage on the 9.7 meg is. I want to know what the voltage on the 4.3 meg is. I want to know what the voltage on the 2 meg is. And then I want to know the total power, and then one other power. I want you to do the power of the 2 meg. Okay? So, we just discussed all of this stuff. Should be super straightforward on how you approach this. Okay? Go ahead. I'll give you some time here. And just as an aside here, John says, what is the acceptable range for answers? It depends. It depends on what the final answer should be. If you get all the other answers correct, I can usually assume you just made a rounding error. If that makes sense. You can always petition to see if you can get credit, but you know, there probably should be some pretty clear evidence. So if you got all the rest of them wrong, but you got this one sort of right, and you're like within, you know, a couple of tenths, then I'm probably not going to count it right, because you know, I've had students show me their work on it and how they got the answer, and I don't know how they got the answer because they didn't even do the calculation on their calculator right. So anyway, I usually go plus or minus a tenth in all my numerical entries. Or, you know, whatever the okay, batteries just died. Hang on a second. I'm going to go change my my batteries for my microphone. Okay, so it's going to go dark for here for a second, but you'll still see the video. Okay, I'm back. For being Energizer Max, they only lasted a week. I was using Harbor Freight batteries, and they last even a little. I was lucky to get a week out of those. Okay, so it looks like we've got a couple of resistors values here. So Steve has found a few of those, and so let me go ahead and find one of these to see if you're on the right track. Now, even though I'm getting ready to solve the total current first, I'm still going to use voltage division for the resistor values, for resistor voltage values, because I think it's important that we just stay on using that technique so you get really, really good at it. Okay? All right. So, and what do I do with my phone? It's right here. So, I've got 500 volts divided by 16 mega ohms. And yes, this time I am putting in the millions. So I'm putting in my exponent on this calculation. So there I've got 31.3 microamps. So I still have microamps. Even though I have all that voltage, I just have so much resistance up against it. Okay, so there we go. So we found this, and this is 31.3 microamps. And so if I utilize some of these colors, does this still work? Nope. That one's done. Where'd my green one go? Did I put it in my pocket? Here's a red one. So, oh, that's the smelly one. Ooh, 31.3 microamps. So that goes around the whole thing. That is for all the resistors because, again, and I'll keep harping on it, there is only one current in series circuits. Okay? All right, so remember, this is, so I see an answer of 31.25 milliamps. And so it should be micro. Remember, this is the Greek letter mu. Okay, so if you were going to report it on paper, you could just say U amps. But I always put the tail out in front because it's technically mu, the Greek letter. Okay. So like if you meant milli, because milli starts with an M, micro starts with an M. You know, it's kind of unfortunate, but use the U if you're trying to distinguish between micro and milli. Okay. So I got a few more calculations coming in. So let's see here. So that's all I found so far. I'm going to go ahead and erase this. Okay. And I'm going to go ahead and write RT just over here in the corner so I have it so I can erase this and have the board space back. So this is total resistance of 16 mega ohms. So I'm going to erase this. And now I'm going to find the individual voltages using voltage division. Okay, so the voltage of the 9.7 meg equals total source voltage, 500 volts, times now the ratio, the individual 9.7 meg over the total 16 meg. Can you guys hear that? The neighbor kids in the background? So for this one, I get 303. Whoops, forgot a zero there. 303 volts. Okay. So I saw some of you did the decimals behind it. 303.125, yeah, that's what I got too, but I still would report this as 303 volts because that's three significant figures. Remember, if there's a zero in between and it's not a leading zero, then it's a significant digit, okay, as far as we're concerned. Okay, so now I've got, so this is 303 volts. Go ahead and do the voltage on the 4.3 meg. So we've got 500 volts times 4.3 meg now over 16. And you can see the ratio right off the bat. This one's going to be smaller than this one, roughly, you know, half-ish, roughly. So change this to 4.3, and now I get 134.4, which I'm going to round up to 3 significant figures, which is 134 volts. Okay, so you can see here, if I were to report 134.4, the other voltage is 303. Who cares about tenths of a voltage when we're talking about, you know, we're approaching 500 volts here total. So these voltage drops are huge, and so we don't need to report the decimals in this case. Okay, so here is a 134 volt, and I'm going to go ahead and grab this space back and do the last two here. And so now the last one here, voltage on the 2 meg is 500 volts, now times 2 meg over 16 meg, which is 1/8. So 500 divided by 8 gives me 62.5 volts. Now this time I am using that because I only have these two digits up here. Okay, so I don't count the leading 0. I report the 3 significant figures for that particular measurement. So there's 62.5. Okay, so now when I add these 3 together, if I separate this out here, so 303 plus 134 plus 62.5, and I get 499.5, which, okay, you know, 500 millivolts away from 500. So that's all in how we rounded this. If we were to round this up to 63 and not even worry about the tenth, then we would get our full 500 volts, okay? But to be consistent, I'm just going to always ask for 3 significant figures no matter what, even though we know that, you know, this decimal has little to do with how it affects the rest of the circuit, okay? So is that what everybody else got here? So 303 and, okay, very good. All right, well, now we only have 2 things left to find here. I'm going to go ahead and get rid of this. And so now I want the total power. Oh, this is the last lecture for this poor new pink one. So the power total is going to be the voltage total times the current total. And so we have 500 volts times 31.3 microamps. So even though we have a 500 volt source, it still only dissipates 15.7 milliwatts. Okay. Okay. And so if you wanted to look at this, you know, I keep alluding to this, and I said something about it just a second ago, but when I look at a calculation like this, okay, in my head, I separate the 2 out. I have 500 times 31.3, and then I also have volts times microamps, okay? So in my head, I'm trying to figure out I'm trying to predict what the unit is going to be, okay? I can tell that this is going to be over. This right here produces microwatts, okay? But this 500 times 30, that's going to give me a number that's more than 1,000, and so I'm going to have to move up 1 from microwatts to milliwatts, okay? Just by looking at this in my head, right? Volts times microamps, that's going to give me microwatts. But this right here is going to give me 15,700. So 15,700 microwatts is 15.7 milliwatts, and that's how I report it. Okay, so that's just something I do in my head. Again, if that's confusing, I try to give you, you know, the way I do it, but then I also give you the straightforward way that will always work for you no matter what. Okay, but these are just little bitty shortcuts that I've picked up over the years. Okay, so we have a total power consumption of 15.7 milliwatts. Okay. Now the last question is, okay, let's look at the smallest resistor and see how much that dissipates. So the power of the 2 meg is the individual voltage drop, so that was 62.5 volts, times the current is the only current, 31.3 microamps. And yes, in this case, I do use the exponents in my calculation. 1.97 milliwatts. Okay. This 9.7 is more than half, and so I would expect that to take more than half of this 15.7. It's probably up around 9 milliwatts, somewhere around there, maybe a little bit less. Okay. Okay, so Valvinder said, could we write the answer as 0.015 watts as well? No, because that, and I know that you just got into the coursework, but we always want to report things in engineering notation, okay? And so maybe I should say a little something about that just to refresh your memory, okay? So hopefully you have these answers here. Let me talk again, because this will be, it's in the first quiz, obviously, if you've already taken it. And I guarantee you it's going to be on the exam, okay? Scientific notation, we always report the number in between 1 and including 1, and up to but not including 10. So the following are valid scientific notation. So 8.23 times 10 to the 4th, okay? 6.77 times 10 to the 5,000th. Or I could have 1.01 times 10 to the negative 11th, okay? Point is that this front digit, just like this, is always between 1 and 10, including 1, not including 10, okay? That's the way your physics and your chemistry classes are going to go, right? Physics does start to use the prefixes, though. But that's scientific notation. I don't want you to report it in that. I want you to always report your number down to and including 1, up to but not including 1,000, okay? So the following are valid engineering notation, okay? 2.45 milliamps, okay? 24.5 volts. 600 microamps, okay? Notice that this number is always between 1 and 1,000, including 1, so I could have 1.01, millivolts, whatever it is, okay? This number here is between 1 and 1,000, including 1, not including 1,000. So it essentially goes from 1.00 all the way up to 999. If your value is not between there, which 0.015 is not, okay? So I want you to report it this way. And the reason why is, if we're working together, and you say, hey, I went and measured that one load, and I got 0.0000152 amps. And so I got to go, oh, geez, how many zeros was that? 1, 2, 3, 4. Okay, move the decimal over. You know, it takes me 10 seconds to figure out and qualify what your measurement was. Whereas if you tell me 2.45 milliamps, I know that's 2.45 thousandths of an amp, okay? This is 600 millionths of an amp. This is 1.01 thousandths of a volt, okay? So I can quickly qualify the measurement based on your prefix, and it's always 1,000 apart, so it's kind of logarithmic in a way, okay? But again, if you're going to move between them, I like to use the mnemonic device: G, capital G, capital M, lowercase k, underscore. That's volts, ohms, amps, whatever. There's no prefix there, and then you go down to milli, micro, nano, pico. Okay, so you got an answer in 0.015 watts. Okay, and so that means you're right here. Okay. And so is the number 0.015 between 1 and 1,000, including 1 but not including 1,000? No. So I need to move the decimal to the right, and so that means I'm going to move over 1 place. So for every 3 decimal places I move to the right, I move 1 letter over. So 1, 2, 3, 15, and in this case, we actually, this is why I wanted the 3 significant figures, is because I think it was 15.7. So if you're going to round it, you should have rounded up to 16 whole, okay? And there went the camera. Somebody time me. Okay, now let me focus it. Sorry about this. And now we come back into our remote shoot. And our live. And there we go. Just got to move it over. Point this at the right spot. And back. All right. I know Steve's got me. How fast was it? Did I make it? Elapsed time. Okay. Let's go back over to the board here. All right. So again, just to reiterate where I was before that shut off. So 15.7. Okay. So I've moved it 3 to the right, and so now I use the prefix of milliwatts. Okay. Now, this quantity and this quantity are identical. If I put the 7 here. Okay. Those are identical quantities, but I want you to give it to me in engineering notation because that's what you're going to do the rest of your college career anyway. And so you might as well get in the habit of doing this now until it just becomes second nature, okay? Any other questions? Oh, he didn't have his timer up. All right, you got to pass this time. Any other questions on this? Let me ask it one more time in the comments here. I don't believe I have anything else for you if we don't have any more questions. Okay, I don't see any. I want to do one more example with node voltages, okay? Okay, no more questions. So I want to do one more example here where we dive more into the node voltages. And this time I'm going to do two voltage sources. Okay. And this one's going to be 8 volts, and this one's going to be 8 volts as well. Okay, so I got 2 voltage sources. So now instead of having the ground down here, which I said is the default for everything that I do, okay, now my ground is in between these 2 sources. And so I'm pulling the positive of this down and I'm pulling the negative of this down to ground, okay? Which means now the bottom of my circuit is connected to, this is negative 8 volts, this is positive 8 volts, okay? Now, if I were just to draw this with a 16-volt source, a single 16-volt source, the calculation for the circuit current and for the individual voltages would be exactly the same. But the node voltages are going to change, okay? So up here I've got, this is, at this node is positive 8 volts. This down here is negative 8 volts. That means I have negative 8 volts here too, okay? So what is the total, if I call this node A and I call this node B, what is my total voltage between A and B, okay? What I mean by this subscript is the voltage of A minus the voltage of B. It's always the first subscript minus the second, okay? And so the total in this case is going to be 8 minus a negative 8, in which case I have 16 volts total in this circuit. Okay. However, the node voltages are going to reflect this being positive 8 and this being negative 8. Okay. But I still have 16 volts total. Okay. Remember, I'm going from negative 8 up to positive 8. That is a 16 volt increase. So I have 16 volts that need to dissipate between these two. Okay. So let's call this, let's just use easy ones, 300 and 400 ohms. Okay. So I want to know what all the node voltages are. So in other words, I want to know, well, I guess there's only one we don't know, right? This one is, we'll call node C. Because this one's B, this one's A. There's only one in between of them, okay? So I go ahead and I find my total resistance here. And I've got 700 ohms total. My total voltage, 16 volts. We already determined that. Okay? So I want to know the voltage drop across this 300. Or I could find this one and then subtract the two. Okay? So 16 volts total. And I want to know the voltage drop across the 300. So 16 volts times 300 over 700. And that gives me the following. If I can find my phone, there it is. So 16 times 300 divided by 700, and I get 6.86 volts. Okay, I'm also going to find this other one. So the voltage of the 400, so 16 volts times 400 over 700. So I got to change this to 400. I get 9.14. Okay. And it looks like that adds up to 16. 6 plus 9 is 15. 86 plus 14 is 100. So that gives me 16 volts total. Okay. So that means that if I take 8, so this voltage drop here, which I'll do in red, give me an excuse to use this one again. So that should be 6.86 volts dropped. And this one should be 9.14. Okay. So I have positive 8 volts here. I subtract 8 minus 6.86 volts. And I have 1.14 volts. So this node voltage is 1.14 volts. Okay? Now look at the voltage drop across this resistor. I always go from the high potential to the low potential. Positive is always higher potential than low potential. Okay? But look at my equation here. I've got, if I want to know the voltage of V, what I would call VCB, from C to B, that's the same thing as the voltage drop across the 400. So VC is 1.14 volts minus a negative 8. And that gives me a positive 9.14 volts. Okay? So you can see there, if I have a different setup with my sources, if I short in between, not short, don't say that, if I ground in between these two terminals here, then this is my positive 8 terminal, this is my negative 8 terminal. Going from negative 8 up to 0 is 8 volts. From 0 volts to 8 volts, that's 16 total. Okay, so again, I could have erased all this and just had a single 16 volt source to find the individual voltage drops. However, it would not have given you the proper node voltages. Okay, so that would be the only difference. The current's going to be the same, the voltage drops are going to be the same, but the node voltages will change based on how you have your setup here. Okay, and so in both cases, it'd be 16 volts divided by 700 ohms, and that should give you your circuit current. Okay.